Hello everybody, Greg is here. I wanted to make a short video about three beautiful molecules which were published very recently. They're not connected, they might be candidates for the molecule of the year 2023. If I missed other molecules you think I should report in this channel, please let me know in the comments. In the next few minutes I'll explain why each of those molecules deserves to be the molecule of the year. So let's start with this one. This is a monovalent tin radical. Tin is under carbon in the periodic table. So there's carbon, silicon, germanium, and then tin. And the normal situation for tin, actually like carbon, is 4 substituents on each tin atom. Also, there's of course already known many stable molecules with 3 organic groups on one tin atom. This is 3-valent tin radical. Also very common is divalent tin. It's not so common for carbon, but for tin it's more stable situation. This one, however, when you take the divalent, so-called stannylene, and remove one of the R groups, such molecules were never reported so far. And this is the first stable molecule of this type. You can see here they built a real fortress around this tin atom here. So it cannot make any bonds with anything around it. Of course, if you keep it without access of oxygen, well, to me it looks like the Star Wars ship. But if you think it reminds you something else, let me know in the comments below. The next molecule has already made a lot of buzz in the chemistry world, published in Nature. This is the first molecule with a chiral center on oxygen. I had a video about chirality when I explained the Nobel Prize 2021. Please check it up. I don't want to go into it. This is really the first one with oxygen. So oxygen usually is divalent. It usually has 2 substituents. To be chiral, you need 4 substituents. And there is a way to make oxygen with 3 substituents by making it charged positively, like it's shown in this molecule, but you cannot make it with 4 substituents. So in order to make it chiral, you have to make these 3 substituents very rigid so it cannot flip-flop. And then you can have this chiral structure. It's like in the screw here. It can be right screw, it can be left screw. And all molecules of this type that were synthesized before, they were all flip-flopping quickly. So in this case, they designed this molecule by adding the R groups which do not let it to flip-flop. And the 4th substituent here is this sort of lone electron pair, which is not a substituent, but it occupies space in the 3 dimensions, and this way this molecule became first molecule with a chiral center on oxygen. They were able to isolate separate stereoisomers by adding a chiral counter anion. Very cool stuff. And the last cool molecule of the day is this porphyrin wheel. Porphyrins are those little square molecules, and they participate, for example, in carrying oxygen in our blood. They participate in photosynthesis in plants and bacteria, and it's pretty challenging and interesting to make arrays of those porphyrins bound together in the way that there's different metals inside neighbor porphyrins. That's all pretty challenging task, although there's some molecules like that were synthesized. In this case, it's just unusually beautiful, and also the chemistry here is interesting. They make this molecule by adding 3 of those parts together and connecting between them. So you have this triple bond here, and it forms a central benzene from 3 large dumbbells of those. That's perhaps one of the largest molecules that were synthesized using this approach. It of course was characterized by many different methods, but especially I like this publication because one of those methods was scanning tunneling microscopy, one of the electron microscopy types. And you can see here the model of this molecule, and it shows that it has 4.7 nanometers in diameter, and by microscopy you see here that the diameters here are pretty close to this value. Of course it will never be exactly the same. A very beautiful work and a very beautiful molecule. Maybe will become become even useful sometimes in the future because of this unique connection of porphyrins. I want to thank everybody for watching this video. Please don't forget to like and subscribe so YouTube will share it with more people. Write in the comments which other molecules you want to see, and don't forget to support Ukraine. Thank you and have a great day.